Hi everyone, we are back with another question this time. The question reads, four identical rods are hinged at their ends to make a parallelogram, ABCD. The hinge joint A is rigidly attached to the wall and the opposite joint C is pulled with A. Initially, the joints A and C were coincident. Find the acceleration vector of the joint B at the instant shown. Okay, let's do some analysis at first, and we may look this angle as theta and this angle must be 90 minus theta. We can say one thing, that for a rod, acceleration at both ends must be equal. This is because we don't want the rod to stretch or distort during this motion. So let's look at the point B. Let's mark its velocity vectors as alpha x and alpha y in the downwards direction. We may notice that the acceleration component across the direction of this rod, let it be alpha vector dot bc cap, okay, and the centrifugal force due to the angular motion, the sum of those two, that is alpha dot bc plus a centrifugal, must be equal to a sine theta. Similarly, if we do an analysis along this direction, we must notice that since A is rigid, the acceleration along the direction of rod at A must be 0. That means the angular accelerations component, that is the centrifugal force here, must be equal to the alpha's component along AB direction. Now we are unaware of what these angular accelerations exactly are. So how are we going to approach this question? Pause the video for a moment, give it a shot, and we'll go back to the solution. Okay, let's look at the solutions now. If we assume each side of the parallelogram to be L, we notice that this length is L sine theta, this length is L cos theta, this length together is 2L sine theta. That means since the acceleration is constant from the equation of motion, we can simply say that distance covered, that is 2L sine theta, must be equal to half a t square, given the initial velocity of point C at the wall needs to be 0. Now from this you will realize that L sine theta is equal to 1 by 4 a t square and sine theta is equal to a t square upon 4L. Now we can also say for the point B that the x coordinate is equal to L sine theta and y coordinate is equal to L cos theta. So this is x, then our velocity in the direction for the point B, that is Vx, must be dx upon dt, that's equal to at by 2, and hence alpha x must be dvx upon dt, that is equal to a upon 2. So this is our first relation. We got alpha x equals a upon 2. Now looking in the y direction, we have y equals L cos theta, Vy equals dy upon dt equal to minus L sine theta d theta upon dt. Now if we differentiate sine theta here, we will obtain that cos theta d theta upon dt must be equal to 2at upon 4L, that's equal to at upon 2L, or d theta by dt must be equal to at upon 2L cos theta. We'll cancel the L's out and we are left with minus at tan theta by 2 to get alpha y is equal to dy by dt. That will lead us to a upon 2 tan theta minus dt upon 2 sec square theta d theta by dt. We know that d theta by dt equals at by 2l cos theta. We will put that here, and we are left with a minus a upon 2 tan theta minus d at upon 2l cos cube theta. Now we are given at square upon 2. Rings a bell? Yes. At square upon 2 is equal to 2l sin theta. We'll substitute that again. A upon 2 tan theta minus 2l sin theta upon l, and we'll break this cos square theta into cos theta, and we are left with sec square theta that we can write as 1 plus tan square theta. This will give us a upon 2 tan theta. Sorry, this must be plus because I've already taken plus out, minus out. So this is plus, and tan theta plus 2 sin theta upon tan theta is tan theta multiplied by 1 is 2 tan theta plus 2 tan cube theta. That means alpha y is minus a upon 2 tan theta, 3 tan theta plus 2 tan cube theta. Hence our alpha vector must be a by 2 I cap minus 3a by 2 tan theta plus a tan cube theta.